and welcome back to the channel. This is CCNA day 14 part 2, of course, because we have spoken about some of the concepts that I'm talking in this video in a previous section. And what I'm going to do is to explain a little bit more so that you can understand this concept better. So let's just go with the first thing. I'm just going to speak about the STP import system, but before that, I want to clarify something. That is very important to understand. That is very, very important to understand. Okay, so the first thing that I want to talk about this is why the loops happen again, right? We did this. We said that, for example, let's say that this is one of the switches in my network. This is going to be another switch in my network. And let's say that I have another switch down here. I have multiple switches, of course, down here, but let's say that there's going to be one of them. And they are connected in this fashion. This is connected to this is connected to this, and also these two are connected to this. Okay, so what happens when something initiates a broadcast inside the network? Say there's a PC connected here, and it just says an ARP message. I told you that what is going to happen is this. The ARP message goes to the switch because the switch does not know where the destination is, so it just floods it out of all its ports except the sender port. That's the rule. So this is going to get to this switch. The switch is going to see this broadcast, so it is going to flood it or send it out of all its ports except the ports that it has received the broadcast from. Same thing happens here. This is going to send it on this port. This switch 1, let's say this is 2, and let's say this is switch 1 is going to receive the broadcast from switch 2 again. So it is going to send it on this port. Switch 3 is going to receive it from switch 1, it sends it on this port, and this goes on, and after some time you can see that this network is completely flooded with these broadcasts that we are sending in the network. So if I have multiple broadcasts from every single device that I have in my network, then just think what is going to happen. The network is going to be full of broadcasts. This is not just the broadcast message. This is not just kind of utilizing all the bandwidth. There's another problem. So switches have some CPUs. One of them is a general CPU. The general CPU handles a lot of different things. One of the things that general CPU handles is going to be the broadcast messages. And when we have a lot of broadcast messages, what's going to happen? The general CPU is going to be overloaded. So during this phase, the switch is going to be completely overloaded with the broadcast message, and the CPU is completely overwhelmed with processing all of these. And when you try to reach to the switch and do something, the switch is not responsive. So the whole network is going to go down in this case. So this is one of the things that we wanted to know about. There is something which is called spanning tree protocol. I spoke about this in a previous video. Spanning tree protocol is going to, what is it going to do? It is going to block one of these ports so that essentially we are not going to have any kind of a loop in our network. So what we have is switch 3 can connect to switch 1 and can connect to switch 2, but it doesn't have a direct connection to switch 2. It goes through switch 1 to switch 2. And how we know that this is going to be blocked based on the election. Let's say that we have just made sure using the priority value that switch 1 is going to be the root bridge. Bridge and switch are the same thing actually, right? In the past we said bridges are switches, but software-based switches actually, but switches are hardware-based switches. Okay, so we know this, and a spanning tree is going to go through some phases when deciding which port is going to be blocked and which port is going to be unblocked. So the port states are like this. This is a classic spanning tree protocol, by the way. Be very careful because you should really know this stuff. The first state is going to be disabled state. In this state, the port is shut down. This is why we call it admin down. So it is not doing anything. It doesn't receive, it doesn't send anything because it is basically shut down. Then we have a no-shut port, which means a port which is up, but it is in blocking state. In a blocking state, we receive BPDUs. We don't care about the data we receive. We just drop all of it. We receive BPDUs, and we check that. the next stage is going to be listening. In this phase, we are trying to prepare ourselves for forwarding. What we are going to do in this case is we just receive the BPDUs, we process them, we know which one of the switches are going to be the root bridge, what is our role in the network, and this is all happening in listening state. We just want to make sure that there is no loop in the network. So listening is where we check for loops in our network. Then after that, when we made sure that there is no loop in our network and the network is stable, we go to learning state. In learning state, we start just receiving the data. We still do not forward it, we just drop them, but we fill our MAC address table. Using that, we will have some information about the network, and after that, we've just moved to forwarding state. In this case, we just receive and send and also learn at the same time. So that is what we have in different states in here. These are essential to understand. You need to know them, and you need to know which one of this happened when. Okay, say I have this switch tree, okay? And say I have not done any specific thing on the port configuration. I'm just going to attach this computer to this switch. What's going to happen? When I attach this, switch is going to notice there has been a change in the port states. There has been a change in the topology. So the switch is going to, first of all, block this port. You can see that the LED on this specific port is amber and flashing. And this means that the port is on, but it is not forwarding any traffic. Then it goes through all these phases. The blocking, of course, is not going to take too long. It's just going to be a millisecond or something. But after that, we see that the port state is listening. After that, learning. And after that, it goes into forwarding mode. And this is going to take some time. I showed you the forwarding timer, right? So that's going to take something like 30 seconds before we can just start, forwarding in this specific port. So we need to wait for some time for that. This is the process that we go through, but after that, we have something which is called convergence. If you remember, I told you that convergence is what happens from the failure up to recovery. Everything in between is a process of convergence, and when the recovery happens, convergence is done. Convergence is finished. So what we have here is this. We have, let's say, something which we call it kind of a freeze in the network. Because the network is not working during this change in the network. So traffic is going to be interrupted. Topology change is going to happen. There are some stuff that we are going to talk about this in more detail later, such as topology change notification, TCNs. And based on that, we can see that something has changed in the topology of the network. And then we are going to start calculating and, sending, receiving BPDUs and stuff like that. And then we can understand which one of the switches is going to be the root bridge in our network, and the rest of the switches are going to act accordingly. But of course, we have some mechanisms to make sure that this doesn't really happen in the network, or if it happens, this is going to happen the way that we want it to happen. Okay, so the next protocol, of course, is going to be one of the most important ones. That's going to be a rapid spanning tree. Rapid spanning tree has a little bit different mechanism than classical spanning tree. If you remember, I showed you how root bridge is elected in a normal switch network, and that was everything that happened in classical, let's say, spanning tree. But now we are talking about something which is going to be a little bit faster than classical spanning tree. Still, some of the rules apply, but now instead of 5 different port states, we have 3 different port states. The first one is RSTP. The first one is discordant, sorry. Discarding is a combination of disabled, blocking, and listening. Essentially, what we have here is the port is not doing anything other than listening to make sure that we don't have any kind of a loop in the network. Then we are going to go to learning, and then we are going to go to forwarding. You can see that we have three states: discarding, learning, and forwarding. So you know already what happens during learning and forwarding, and discarding, of course, does not do anything other than just listening to the network. So this is kind of a simplified model. But in RSTP, what we have is a mechanism in which that the ports try to talk to each other, and there is something that we call it a proposal and an agreement. And based on that, eventually we are going to learn which one of the switches is going to be the root bridge and which one is going to be the subordinate bridge, and they are going to cascade down so that the network is going to be created based on the topology that we have decided. Port roles, of course, are going to be a little bit different, as I showed you before in the practical part. So we have the root port. That's going to be the port that, kind of points to the root bridge in our network. We have designated port. That is the forwarding port in a segment, as I showed you. These are the same as what we have using with classical spanning tree. Then we have alternate port. So alternate port is going to be in blocked state, but it is there, and we just call it whenever there is a problem in the actual root port. If root port goes down for some reason, alternate port is going to replace, and this replacement is going to happen super fast. It is not like it takes some time. It just goes super fast from this state into let's say what we call it forwarding state. And finally, we have backup ports. This means that we have backup ports at the same segment. So alternate ports replaces root, backup ports replaces designated port actually. So these are the different port roles that we have in here. Also, I already told you that switches talk to each other, and this process is very much similar to a handshake. And instead of just using timers, like I said, there is something that we call it proposal and agreement. So this means that each switch sends the proposal to the other switch. So the other switch is going to check to make sure that the proposal that it has received is from a superior switch or from an inferior switch. So a superior switch is a switch which you believe that is going to act as a root switch. Why? Because it has a better MAC address or better, let's say, priority. And you know that in layer 2, most of the time, the lower is better. So most of the time, you're talking about ranking, not just the amount of value that you have assigned to a port or, let's say, a switch or something like that. But on the other hand, something which is important to understand is RSTP is compatible with classical spanning tree. So if one of the ports, for example, on a switch is connected to another switch that doesn't understand RSTP, that specific port is going to act using classical spanning tree. Okay, so we have spoken about some of the stuff that we are talking in here. So we went through the election of root bridge. Then we spoke about each non-root switch, the election of root port on a non-root switch. I told you that all the ports on a root bridge is going to be a designated port because they have to be forwarding. Non-root switch or the other switches, actually, they are going to select one of their ports as root port based on the cost. Cost is important to remember. And then we are going to have designated ports per segment. The rest of the ports all of them are going to be in blocked state. So finally, what we are going to have is going to be a network which is totally converged, and everything is working just fine. Also, like I showed in previous section, you need to be able to recognize which one of the ports are going to be root ports, which one is going to be designated port. And if you understand this, most of the exam questions about spanning tree is going to be super easy for you because you really understand that in that case. Okay, what happens if spanning tree fails, right? So once again, when we have a spanning tree failure, what happens? I showed you that we have this triangle topology in here, and switches are connected in this fashion. Let's say switch 1, come on, okay, switch 1, switch 2, and switch 3. And I told you that spanning tree is going to block one of these ports. Let's say, for example, this one. Now let's say that this port is not blocked. Then again, we have that broadcast storm problem that we had, and frames are going to start flooding the network. The network is going to be overwhelmed. CPUs are going to go high. And something which is very interesting is called MAC address flapping. MAC address flapping, MAC addresses are learned through one port, then they're going to be learned through another port, and that is going to change the MAC address table on and on and on. So say, for example, a broadcast has been initiated from here. This goes up here and up here. Switch 1 is going to receive it based on the MAC address of the sender. It's going to write the MAC address table in here. Says, for example, on port 1, I have MAC address A something. Switch 2 is going to do the same thing. So it says that, okay, I have received this broadcast and I'm just, populating my MAC address table. I understand that on port 1, for example, I have this MAC address A. And it's a broadcast, so it's going to be forwarded this way. 1 is going to forward it this way. Then when switch 2 sends the broadcast towards 1, it's going to see that the broadcast, the MAC address, which was previously on port 1, now it is on port 2. So it's going to delete this one. It's going to change it to 2 and says that A is in here. Same thing is going to happen on this switch. It's going to say, okay, A is on 2. Then this is going to send it this way. Switch 3 knows that the port connected to A is that, but now it is receiving the broadcast from here, so it is going to update the MAC address table. So it is going to happen on and on and on. So this is going to be deleted. It just goes with 1A, then deleted to 2A, then deleted, and on and on and on. So this is called MAC address flapping. That's the problem, right? This is another issue that is going to raise the CPU load in here. So you can see that CPU hits 100%. Switch is unresponsive. You cannot do anything other than going to the switch, just unplugging some of the ports, and then making sure that those ports are not working. And then after that, you just, fix the problem of the spanning tree and see what is going on. And the best, of course, thing to do is to understand how spanning tree, verification commands work. So let's just go to the topology that we have in here. This is the topology, and of course it has to start. So in this topology, as you can see, I have some PCs connected to here. So this is, I'm just going to initiate something from PC 5, which is connected to, I believe that this is VLAN 20. Let me see. So let me just go to PC 5, and I'm just going to say IP address. It is IP 10.10.15.5. So this is connected to VLAN 15. So now if I just say ping 10.10.15.7 and hit enter, this is going to have some responses, which means that now switch 3 understands where this PC5 is. If I just go to switch 3, for example, and say show MAC address table and hit enter, it says that I have received something on port E11. On port E11, this is the MAC address, which is on VLAN 15. So we have known this. This is a unicast message, so there's no problem with that. But if it was a broadcast message and the spanning tree didn't work, then we would have a lot of problems in here. Let's go to switch 1. On switch 1, what I'm going to do is to say en show spanning tree, and specifically I'm just going to see a specific VLAN, so VLAN 15, for example. Hit enter, and based on this, it says that I am the root for VLAN 15. This is VLAN 15, as you can see. I understand that this is per VLAN spanning tree, although you see IEEE. The priority is 32,000. I have not done anything about this to change the priority, but this is the root based on MAC address. My MAC address is AABBCC0000100. which happens to be the lowest MAC address in the network, but this is non-deterministic as I told you. I'm going to change this after some time. And then it says that this bridge is root for V915. You can see the timers. Every 2 seconds, there should be a BPDU in the network. The max age is 20 seconds, which means that if I do not receive a BPDU, I'm just going to wait for 20 seconds. And after that, I will initiate a topology change notification. I would say that I have not received anything, so this is going to happen. The convergence should happen here. There's a failure. A forward delay is 15 seconds, which means that for listening, I'm just going to wait 15 seconds. For learning, I'm going to wait 15 seconds, and then it's going to be 30 seconds before I go to forwarding mode. If I just go to switch through and check the same thing here, I'm just going to copy this command, go to switch to, go to enable mode, and then paste this command. You can see that it says the root ID is this one, which was for switch 1. My ID is 0200. Switch 1's ID is 0100, and it says root is 0100, which is exactly the same thing. This is why we see this sentence here that says this bridge is the root, right? But on switch 2, of course, this is not the case. It says that the root is 100, but I am 200. You can see that because we are in VLAN 15, now this is going to be added to VLAN as the priority number, and it's going to give me the priority of 32,783. So if I just say VLAN 1, so you can see that the actual priority is going to be, oh, we have changed this for VLAN 1 actually. We didn't change this for other VLANs, if you remember that. So that's what we have in here. Well, but these are the change value. Well, priority by default on the port, and the VLAN number is going to be added to that, which is called a system ID extension in here. Now you can see that the port rules are obvious. A port could be in designated port. Designated port are always forwarding. Then we have root ports, that is always forwarding. Designated port, again another one, which is always forwarding. This might be for a section. And alternate ports are always blocking, but they are there to transition into forwarding mode in a few, and I wouldn't say seconds, I would say sub-seconds actually. So show spanning tree is going to show you the root bridge, the roles of the ports and the states of the ports. You can check them for each one of the VLANs separately. And you can see which one of the ports is in blocked mode that should not be forwarding. So based on that, you can just change the topology. You can just remove some of the cables and add connect some of the cables, and after that you're going to have a stable network. So the final thing is the design is very important. You need to be very careful about the design of your network. So everything that you do in the beginning is going to determine what is going to happen in the network. It is not all about configuration. It is about the design of the network, and that is going to minimize the amount of emergencies that you have in your network. So be careful about root bridge in your network. It should be deterministic. You should define it. You should say which one of the switches should be the root bridge. Secondary and primary bridges should be configured. I have done this in a previous video for VLAN 1 only, but later we are going to divide the VLANs into groups and then choose which one of them is going to be which is going to be root for that specific group of VLANs. And do not just leave it to the chance. So you should not really have a network that everything happens in that network for on itself. So that is important. And spanning tree design should be documented so that based on that document you can understand what is happening in the network. So that's all about this video. I hope you have liked this video. Like it, share it, and subscribe to the channel, and also hit that bell button so that you're going to be notified whenever there is a new video. Also, there's a thanks button. I will appreciate you pressing that button as well. Have a good day, and see you in later videos.